Hello, my name is Tyler Bowman, and I'm going to be going over my project for ECE556, which is on SAR target classification, a hybrid deep learning approach on the MSTAR dataset. Okay, to start things off, we're going to give a brief introduction on what is SAR, the importance of SAR for target classification, some challenges in SAR for target recognition, and then overall kind of the objective of this project, and then some recommended reading material. Okay, so what is SAR? SAR is synthetic aperture radar. It's essentially an advanced remote sensing technology that uses radar pulses to create high resolution 2D and or 3D images. And it's typically defined in the RF frequency bands, X band, C band, S, L, and or P band. So that's essentially from 12 gigahertz down to 300 megahertz with associated wavelengths of 2.4 to 100 centimeters. Some key advantages to using SAR is that it works in all weather conditions, unlike like optical sensors, which rely on sunlight. SAR can also penetrate through clouds, rain, and smoke. So ideal if you have it essentially on a satellite. You can still map the ground and different things on the Earth's surface, basically in all weather conditions. And it also works via day or night, due to the active illumination of the radar system. It's also used in military and civilian applications, primarily for surveillance, disaster monitoring, and terrain mapping. And then to go over some challenges in SAR target recognition, some of the ones highlighted that I wanted to highlight were noise, speckle, and variability of target poses. So what is speckle? So speckle, essentially noise, is a granular interference due to bouncing properties of emitted radio waves that degrade the quality of the image and therefore more difficult to interpret to the human eye. And so you can kind of equate it to static on an old TV, right? Also, target poses variability. So essentially, if a target's radar signature changes dramatically with the viewing angle, i.e. a tank looks different at 15 degrees versus like 45 degrees. So kind of depending on how the target's orientated and how the sensor is capturing that can make it challenging for recognition, as we'll see. Also, clutter and camouflage, or targets blend into the background clutter, i.e. forest, urban areas, right, make it difficult to kind of isolate it. So that's another kind of challenge. So with all these challenging demands, it kind of calls for robust algorithms, right? So kind of traditional methods like SVMs or PCAs, they struggle. But with hybrid deep learning, combining like CNNs for spatial features and transformers for contextual relationships can greatly improve the accuracy. And that's kind of where the work in this project begins, is kind of, what are some things that we can do from a hybrid deep learning perspective. And then just one footnote here, the recommended book here that's shown in the picture, The Essentials of SAR by Thomas P. Yeager. It's a great great starter book for someone who's interested in learning about SAR, who's maybe not an electrical engineer. Okay, so I wanted to briefly go over the MSTAR dataset and kind of what it contains. So it stands for Moving and Stationary Target Acquisition and Recognition. The dataset, the images were taken with an X-band radar system, and it includes multiple targets. In this case, we have 8 target classifications. So it includes tanks, trucks, BMPs, and another target called SLICE, which I'll go over in a second. It also includes different depression angles and aspect views. Primarily, I use the 15 and 17 degree depression angles. And then I'll kind of give an overview of why I use this data set for automatic target recognition. So going back to the SLICE target classification, essentially this stands for Simple Lightweight ISO Containers. It's really a synthetic target, primarily for benchmarking, algorithm validation, and some other kind of controlled experimentation stuff. So it's used really to calibrate the SAR-ATR systems, and it's kind of included in the data set along with the other real world targets. So yeah, as mentioned, this is a high resolution SAR imagery. The data was collected by Sandia National Labs with their X-band radar sensor. And its resolution is essentially at 1 foot of resolution. And it includes realistic backscatter signatures under controlled conditions. It's a pretty diverse target set and great to use it in this project, which is why I selected it. It really lets research reliably train, test, and compare their target recognition algorithms. So much research was done to understand SAR and its uses, as well as looking at automatic target recognition and what are some of the current models out there, what are some of the techniques used, also looking at the different data sets that some of these research papers are using to better have a better understanding of where I should head for this project. So it's so SAR ATR has really been a long-standing area of research. And I'm not going to go through all of these, but I just wanted to highlight 2 of them. So paper number 2, which is the benchmarking deep learning classifiers for SAR automatic target recognition. So this paper basically went through 3 different CNN variants, ResNet 18, 34, and 50, as well as a graph neural net network and a small data vision transformer across 3 different target data sets, MSTAR, GPSAR, and synth-awake SAR, to assess not only classification accuracy, but also inference speed and resource requirements. I thought this was really kind of useful since this is kind of where I was tending to head towards my project and kind of doing a comparison analysis with my proposed hybrid solution. And the results showed that the GNN excels in throughput and latency, while no significant architecture outperformed across all the different metrics, underscoring the need to choose models based on specific deployment constraints rather than just raw accuracy alone. They basically, concluded that, one model rules all type of solution is unlikely for SAR ATR and calls for more diverse public data sets to guide model selection. And the last one I wanted to highlight was paper number 4, which the paper tackles the challenges of polarimetric SAR, or POLSAR as they call it, image classification, where the data are rich but label samples are scarce, and they proposed a multi-granularity hybrid CNN vision transformer architecture that fuses both local and global features via external tokens and cross attention, which I also found was useful for this project. So this describes the proposed hybrid deep learning model. In a nutshell, so the core of the model architecture is utilizing a CNN, or a convolutional neural net, plus a vision transformer. And for the CNN, I decided to use MobileNet v3, which initially was developed by Google in 2017. And then there's been a couple different variants over the years, with MobileNet v3 as the latest officially released, but the v4 is soon to be released officially. And its architecture builds on deepwise separable convolutions and inverted residual blocks. And it uses lightweight attention via squeeze-in excitation and the hard-wish activation for extra nonlinearity with minimal cost. So it's really strong in highly optimized. Well, it's really strong for low compute and mobile inference, with strong local feature extraction and built-in inductive biases. So, i.e., translational invariance and locality. And then the second part of the architecture is the vision transformer, which was also introduced by Google. And my particular implementation is a pre-trained VIT model from Hugging Face. And this architecture splits an image into fixed size patches, linearly projects them into tokens, and then processes the sequence through a standard transformer encoder layer with a multi-head self-attention block. Where this type of model is strong is basically it has a global receptive fields, so it's able to model long-range dependencies and cross-patch contexts at a cost of higher compute though, and general larger data requirements. So those are kind of the two main backbones, if you will. And then there was also I developed a classification head, which essentially does an input processing portion and then a feature extraction. Then I basically fuse that into a feature fusion portion, and then that includes a projection to common dimensions as well as a concatenation. And then there's a classification layer at the end, which has a dense layer that outputs 256, as well as regularization that includes batch normalization and dropout, as well as a final softmax layer. And basically, hybrid CNN vision transform architectures can give you kind of the best of both worlds, right? So it can implement. It leverages like MobileNet v3's ability to pick up edges, textures, and fine spatial details with very few parameters, as well as kind of the global contextual model via self-attention in a vision transformer. Let every patch attend to every other patch, capturing long-range dependencies, which is pretty critical. So I'll briefly go over the model requirements of this project. The main things I wanted to focus on were accuracy, how well does it generalize, the inference speed, and the lightweightness of the model itself. Followed by, I'll go over the algorithm design approach that I took for this project, as well as the overall system architecture, kind of showing the internal design of the hybrid feature extractor. So for model requirements, so obviously wanted to prioritize the performance, and I used the accuracy metric to determine that. And then wanted to see how well it generalized given new data, new target data, as well as how fast can the model operate. So how quickly can it output predictions, as well as its ability to be lightweight and efficient to run on like mobile edge devices. And then for the kind of the main approach for the design that I took was kind of equivalent to a spiral design methodology with two primary iterations. So essentially I would evaluate the model's performance against kind of a predefined spec, so kind of like a pre-trained model. And then I would go into an improvement training strategy process based on the outcome from the previous iteration, and then it looked to optimize and tweak different either hyperparameters or different aspects of the model itself via freezing or unfreezing different layers. And then I also, as a side aspect of the project, wanted to explore few shot learning, and I used essentially a Siamese network architecture to do that. And then from a system architecture, so here, the picture here shows kind of the internal design of the feature extractor, where you essentially feed in the input, and then it kind of runs two parallel paths. One goes to the vision transformer, the other one to mobile VNet v3 CNN. Then there's a global average pooling layer, and then it does a concatenation, and then outputs into a dense layer with batch norm and dropout parameters as well, and then it basically outputs the embedding at the end and makes a prediction on the target classification. So the general methodology that I took in developing this model. So first, the data had to be pre-processed. So it essentially all of the target data came in single-channel grayscale images. Essentially had to normalize the pixel values and apply a uniform kind of resizing, because that was the requirements for the two models that I chose. So it's essentially 224 by 224 by 3. So essentially I load the image in the labels, convert to NumPy arrays, and then I had to do a split of the data. So I split it, the training, validation, and test, basically did an 80% for training, a 10% for validation, and 10% for test. With each split respecting each original class balance, because there was a slight imbalance in the classes. And then essentially did a fixed random state of 42, basically. So every time I run the script, I'd get the same results every time. I also had to encode the labels. Had to use one hot encoding for the labels, and as well as the second. The second thing was data augmentation. So this is where the project really showed its robustness, because some of the pre-trained models performed quite well with no data augmentation, which goes to say, was it overfitting the training data. So essentially what I wanted to do was add as much data augmentation to see how well each model performed. So that included randomly rotating the images, shifting them, zooming in, affecting the brightness variation, as well as flipping images. And so and also not mentioned here, but I also kind of researched more SAR specific augmentations. So, and 3 of those that I wanted to focus on were shear transforms, basically tilting and slanting. It does like a tilting and slanting effect on the images. The brightness, which kind of I mentioned, that helps the model adapt to varying signal intensities and illumination levels. And then contrast adjustment, which is useful for simulating sensor level intensity or phase changes in the radar images. So those were kind of the main things. And then for model training, I basically had a kind of 2-stage training strategy. Initially, I wanted to freeze the transformer, freeze all layers of both the CNN and the transformer. And then essentially after running that, I basically wanted to fine tune it. So I tried tweaking with unfreezing some of the layers more towards the end, because I found that was more beneficial. And then also I looked into mixed precision training, dropout, and batch normalization. So all those things really are to help fine tune some of those parameters, and had different combinations of each, but found kind of from a batch size, I found that batch size of 16 was kind of ideal for this data. And then looked at a couple different optimizers and loss functions, but ultimately narrowed down to atom for the optimizer and categorical cross entropy for the loss function, which is ideal for one hot targets. And then for evaluation metrics, as I mentioned before, accuracy was the primary. And then I also did a confusion matrix as well as a classification report using precision recall and F1 score. So for the experimental setup, the software, so I was developing in Google's Colab environment, using primarily Python as the language of choice. For the hardware, leveraged NVIDIA's Tesla T4. As mentioned, the training validation test split is there. For the models, basically for the baseline models, standalone, I used 4 different variations of the CNN, so the MobileNet V3, and then 1 model variation of the transformers, just given some time constraints. And then for the hybrid model, I had 3 variations of my optimized CNN transformer model, and then 1 model variation at the end, which implemented a Siamese network with a hybrid with the same hybrid backbone as mentioned before. And then I plotted the results, accuracy over epochs for each of those to see how they compared. The next 2 slides go over the results and analysis portion of the project, which primarily were quantitative in nature. So this first slide here goes over a comparison table of all the model variations with and their effects on data augmentation, and then their performance test accuracy. So as you can see, the results are greatly impacted whether or not data augmentation was fully applied or partially applied. As you can see, the pre-trained vision transformer model number 5 and the hybrid CNN vision transformer model number 6 achieved greater than 99% accuracy even without data augmentation, highlighting their strong baseline performance on this MSTAR clean data set. Surprisingly, fine-tuning the MobileNet V3 small model number 3 with partial augmentation outperformed its full augmentation counterpart, model number 2, which was quite interesting. However, with full data augmentation, which was kind of the main objective of the project, Model number 8, which was the proposed hybrid CNN vision transformer, maintained 99.16% accuracy, demonstrating how robust really it was to the augmented data. And then, based on these results, okay, well, why was model number 8, why did it excel amongst the other variations? So basically what I think is that combining the local feature extraction from the CNN as well as the global context modeling from the vision transformer essentially made it the most resilient to augmentation, so like induced distortions and other aspects to altering the target itself. I think that's why it performed the best. And really fine-tuning preserve pre-trained knowledge while adapting to the MSTAR's unique STAR features was also another aspect. So something that was unexpected was that the fine-tuning with full augmentation, model number 2, really collapsed at only 13.09% accuracy, and could be potentially from the overwhelming noise from a small model, but not 100% sure why that was. It would need further analysis. And then the last one there, number 9, was essentially the Siamese network, which achieved pretty decent results at 97.04 without augmentation, though. Kind of showcasing at least its somewhat promise for few-shot learning with which is critical for scenarios with limited labeled data. So I think the real big takeaway is here that it was that the hybrid model was actually quite an optimal choice for this SAR target recognition at the 99.16 and showed very good robustness in the presence of data augmentation. This is the part 2 of the results and analysis, which just shows the correlating results for the model number 8. So this is essentially the accuracy graph, if you will, over epochs, as well as the confusion matrix and the classification report, which has the precision recall and F1 score. As you can see on the confusion matrix at the top right, it really only miscategorized 2 of the T62 targets and 6 of the ZSU 23-4 targets. So I think overall it actually performed quite well with just a couple minor misclassifications. To validate the overall effectiveness of the proposed hybrid model, I conducted a comprehensive ablation study, really analyzing 3 main aspects: impact of different components in the architecture, the effect of data augmentation, as well as hyperparameter sensitivity analysis. So with the impact of different components, mainly I wanted to systematically remove key components and then assess their overall contribution to the classification accuracy. And one kind of key insight was that the convolutional neural network excels at the local feature extraction. So, this could be the edges or the corners of the target, while the vision transformer captured the long-range dependencies. So, most likely the target shape and the orientation. And that cross attention is critical for blending kind of both of those strengths together. For the effective data augmentation, kind of highlighting kind of an overview, the tested augmentation strategies to improve generalization in low data regimes. The main key insight there was that physics-based synthetic data significantly improves the performance in these adverse conditions, where the moderate augmentation, whether it's rotation or speckle noise or some of the other various parameters, they offer a good trade-off for real-world, real-time systems. And then the last one being the hyperparameter sensitivity analysis. So this kind of focused mainly on learning rate scheduling and batch size sensitivity, which I found that a batch size of 16 and then an exponentially decaying learning rate yielded the most stable training dynamics. So during system design, several challenges were addressed to ensure robust SAR target recognition. So some of those limitations and challenges are noted here. So one of the biggest things is the small data set size, right? So roughly dealing with 9,000 images, SAR images, across 8 target classes, and not all the classes have the same number of targets, so there was a class imbalancement there. And one way I dealt with that was through stratified sampling as well as targeted augmentation. The other thing was limited viewing angles, so only having access to the 15 and 17 degree depression angles. So opening that up more would just increase the robustness of the data set. And then finally, the SAR specific noise. So that's mainly the speckle noise and structural variations, which are introduced via the intra-class variability. So those are kind of the main things with the data set. As far as computational complexity, this was another big one. One way I mitigated this was, first of all, using lightweight models, which was, the main intent on using MobileNet v3s, the small version, as well as requiring mixed precision as well as gradient checkpointing for the training optimization. And then finally, the generalization to unseen targets, which is why I included the synthetic target, which adds further variation, making the class boundaries more complex. So some of the things I didn't quite have time for, just given the limited time frame for the project. Some things I'd want to look at in the future would be enhanced data augmentation for these adverse environments. The current augmentation that I use may not fully simulate real world SAR challenges like extreme weather or clutter. So I'd want to definitely look at more physics-based simulations and adversarial training to further go into that. Also was really curious about explainable AI for SAR classification. So with black box deep learning limits trust in these more military defense applications. So it would be interesting to use like the shape and lime algorithms, do that analysis to kind of identify which features of the model relies on the classification the most. And then thirdly, the real-time deployment on edge devices. So this could include model pruning, additional quantization, as well as knowledge distillation. And then finally, the scalability for resource-constrained environments. So really, this is to support more field deployment on training devices, and then things that are more hardware aware. So basically, we'd have to do more neural architecture search to kind of further optimize more efficient models for specific hardwares. In this project, I investigated deep learning techniques for synthetic aperture radar target classification, leveraging the MSTAR dataset to evaluate model performance under real-world conditions. The proposed hybrid CNN vision transformer architecture achieved an exceptional 99.16% accuracy, surpassing the standalone models by effectively combining the CNN-based local feature extraction with the vision transformer's global contextual understanding. To address the challenges in low data environments, I implemented a Siamese network using the same hybrid backbone, achieving roughly 97.04% accuracy on unseen image pairs, demonstrating strong potential for few-shot learning in scenarios with limited labeled data or dynamic target sets. The key strategies to overcome SAR-specific hurdles, such as data scarcity, class imbalance, and overfitting, included transfer learning, advanced data augmentation, and mixed precision training. These approaches not only improved the model's robustness, but also established a scalable framework for future research. So thus, in conclusion, this work underscores the viability of hybrid deep learning models for SAR target recognition while paving the way for future optimizations in real-time deployment, explainability, and generalization to more complex operational environments. And these are the list of the references for this project. This concludes the presentation. Thank you for your time and attention.